Hello, team. My name is Brett Gustafson. I'm a wireless business developer here at Altera. And today I'll be presenting a demonstration by Ankur Vora, a network system solution engineer at Altera. I'm excited to present our innovative approach to channel estimation using convolutional neural networks, or CNNs. This slide discusses the role of channel estimation in signal processing, as shown in the diagram. The diagram illustrates the relationship between transmitted signals X and the received signals Y through a channel matrix H with added noise N, as the equation Y equals HX plus N. For simplicity, we're showing a 2T, 2R MIMO system. But for massive MIMO systems like 4T, 4R, and above, know that this matrix scales exponentially. As shown in the diagram, channel estimation involves three key aspects: channel analysis, analyzing how the noise affects wireless signal; performance impact, assessing how channel conditions impact overall system performance; and lastly, noise assessment, evaluating the level of noise interference in the channel. Here, we compare and contrast standard approaches for channel estimation relative to AI-based methods. Standard approaches for channel estimation often rely on more pilot symbols, leading to overhead. They perform poorly in low SNR conditions and are highly sensitive to noise. Techniques like least square and minimum mean square error are commonly recommended by 3GPP, but also have their own limitations. Their complexity grows along with antenna counts, like in massive MIMO implementations. AI offers a transformative approach, enhancing adaptability and robustness in complex conditions. It enables accurate estimations with fewer resources, improving efficiency and reducing overhead. As we move towards more advanced networks, AI-driven channel estimation stands out for its ability to adjust dynamically to varying channel conditions, ensuring reliable performance even in high-noise environments. Let's take a high-level look at the overall wireless system architecture. We begin with a link-level simulation. Using MATLAB, we generate a 5G NR-compliant TDLA, or tapped delay line A, channel mode for both uplink and downlink communication. This step is critical for emulating real-world propagation conditions in a controlled environment. Next, we have CSI, channel state information processing, at the UE, or user equipment. Here, the UE performs measurements and computes key parameters such as RS, RP, which is reference signal received power; RSSI, which is received signal strength indicator; and RSRQ, which is reference signal received quality. These measurements form the basis for accurate and timely CSI reporting back to the network. Now let's focus on the wireless channel. The signal traverses through various propagation models, including line of sight, or LOS, non-line of sight, or NLOS, cluster-based models, and TDL channel models. These simulate a range of real-world conditions from ideal to highly obstructed environments. Finally, we arrive at the CSI processing, which occurs in the radio unit, or RU. The RU uses the CSI feedback received from the user equipment, UE, to make scheduling decisions for downlink transmission. This ensures that the radio link is optimized for current channel conditions. This slide represents the convolutional neural network CNN architecture used for channel estimation, as illustrated in the diagram. We begin with data generation. Here we generate a 5G 3GPP release 17 compliant CSI data using the MATLAB 5G toolbox. This dataset provides the foundation for training and ensuring that the model captures realistic channel behavior. Next is pre-processing. To prepare the data for inference, we separate the real and imaginary components of the complex CSI data. This step is essential for compatibility with AI frameworks, which typically operate on real-valued inputs. Moving on to the model training, using the MATLAB Deep Learning Toolbox, we train the CNN to learn and generalize from wireless channel data. The architecture includes convolutional layers with a 5 by 5 kernel size, 32 filters, and ReLU activation functions. This setup enables the model to effectively capture spatial correlations with CSI data. Finally, we arrive at post-processing. Once the CNN outputs are generated, we recombine the real and imaginary parts to reconstruct the complex valued channel estimates. As shown in the diagram, this end-to-end CNN pipeline provides an efficient and accurate method for channel estimation, capable of learning and adapting to complex wireless environments. This slide outlines the experiment setup and results, as illustrated in the diagram. It details the hardware and software environment used in the experiment and presents a comparison between the AI-based and traditional channel estimation techniques. Starting with the experiment setup, we utilize the Altera SoC development kit as our hardware platform. JTAG was used for device programming, UART for debugging, and Ethernet for data transfer. The software stack included FPGA AI Suite for interfacing with the AI IP blocks, Quartus Prime Pro for FPGA synthesis and programming, and the OpenVINO model optimizer to convert and optimize AI models for hardware development. On the right, we see a throughput versus SNR graph, comparing AI-based estimation, which is the blue line, with traditional estimation, the red line. The x-axis shows SNR values ranging from approximately negative 20 dB to positive 20 dB. The y-axis represents throughput in megabits per second. As observed, both methods perform similarly in low SNR conditions, where noise dominates. However, at high SNR levels, the AI-based estimator significantly outperforms the traditional approach. This gain is emphasized by the red circle on the graph. In summary, this experiment validates the superior accuracy and efficiency of AI-based channel estimation, particularly in high SNR environments, where it delivers notably higher throughput. Here, you'll see two synchronized visualizations. On the left, we have the MATLAB-based simulation, which models the end-to-end wireless communication system. And on the right, you'll see the AI Suite inference visualization, showcasing real-time performance of the AI-based channel estimation on hardware. A key metric displayed here is error vector magnitude, or EVM, which quantifies the distortion between the transmitted and received signals. The lower the EVM indicates higher signal fidelity. As results show, AI-based estimation consistently achieves lower EVM than traditional methods, clearly demonstrating superior signal quality and estimation accuracy. As we wrap up this presentation, we hope you found our insights into AI-driven channel estimation both informative and thought-provoking. I want to thank you for your time, attention, and interest in our work, and I welcome any questions you may have and look forward to engaging in further discussion on this exciting and evolving topic.